Algebra 3, Chapter 2, Section 7, Inverse Functions. Remember that a function takes an x value and sends it to a particular y value. The inverse reverses that process, that is, it matches the y back to the x. Here's some examples. Addition and subtraction. X plus 3 minus 3 gives you back to x. Multiplication and division. 2 times x divided by 2 gets you back to x. A square and a square root. They cancel each other out. When you compose two inverse functions, they will cancel and leave you with just x. Graphically, an inverse is a reflection of the original function across the line y equals x. So we're going to sketch the inverses of these graphs. So here's one graph. Okay, we're going to draw the diagonal line y equals x. And then we're going to just sketch the reflection. Notice they're going to intersect on the line y equals x. There you go. Okay, now this one, same thing. We're going to draw our line y equals x, and then we're going to reflect it. And notice here where on the original function we had the point 0,1, now we have the point 1,0. And again, you see that they're intersecting at that line, y equals x. A function whose inverse is also a function is called one-to-one. That means that each y value can be traced back to only one x value. So each x gives you exactly one y, and each y comes from only one x. Graphically, we use the horizontal line test to determine if the inverse is a function. So if we want to know if a relation is a function itself, we use the vertical line test, and each vertical line can only intersect the graph in one spot. If we want to know if the function's inverse will be a function as well, then we use the horizontal line test, and the same rule applies. You draw a horizontal line anywhere through the graph, and it can only hit the graph in one spot. Now again, if it fails the horizontal line test, that means the inverse is not a function. The original will still be a function if it passed the vertical line test. Okay, to find out inverses algebraically, first of all, you need to verify that there is an inverse function to find using the horizontal line test. Then all you do is you switch x and y, and you solve for y. Now, I'm going to show you an example, and this is really probably as complicated as they're going to get. So in a sense, we're starting with the hard ones, and the rest should be easier. So here's the first thing we do. We take f of x equals 5 minus x over 3x plus 2, and we change it to x equals 5 minus y over 3y plus 2. So we just swapped out the x's and the y's. Here's where it gets interesting. We're going to multiply both sides by 3y plus 2. So we have x times 3y plus 2 equals 5 minus y. And then we're going to distribute. So we have 3xy plus 2x equals 5 minus y. Now here's the key. Get everything that has a y attached by multiplication, or if it's just a y by itself, get those on one side. Everything that doesn't have a y attached goes on the other side. So that's the next step. We have 3xy plus y equals 5 minus 2x. Notice 3xy plus y has a common factor of y. That's why we did it. So we factor out the y, and we get y times 3x plus 1 equals 5 minus 2x. And then just divide by 3x plus 1, and you're finished. Now sometimes we need to treat a relation or an inverse like a function even though it isn't. And when this is the case, we do what's called restricting the domain. In other words, we limit our choices for x so that the resulting graph or the inverse will be a function. So this is where you'll have a problem and they'll say x can only be these numbers or x can't be these numbers. What they're doing is they're restricting the domain to allow the equation to be a function. Okay, here's a problem to try. You're going to use the graph of this function to sketch the graph of its inverse. I know it's a little hard to do. See if you can maybe replicate this on a piece of graph paper to try it. Pause the recording, give it a try, and resume to check your answer. Okay, there's our inverse. Notice it's reflecting across the line y equals x. Okay, for our next example, we're going to verify that f and g are inverse functions both algebraically and graphically. To verify it algebraically, you're going to compose them and your result should just be x. It's important to show your work here. That's how I know that you knew what to do. And then graphically, we're going to show that they are reflected across the line y equals x. Pause the recording, give it a try, and resume to check your answer. Okay, so here we have them composed. We're going to put the cube root of 8x in place of x and f, which gives us the cube root of 8x cubed over 8, or 8x over 8, which is x. When we compose them the other way, we have x cubed over 8. We're going to multiply that by 8 and take the cube root. The 8's cancel. We have the cube root of x cubed, which is just x. And then b is the graph, and you can see that they do indeed reflect each other across the line y equals x. Here's another one to try. Pause the recording, give it a go, and resume to check your answer. Okay, it looks a little messy here, but you can see that when you compose them, you do indeed get x for both. And the graph is a reflection across the line y equals x. Now you're going to use a graphing utility to graph the function and use the horizontal line test to determine if it has an inverse. So really you're just graphing and saying yes or no. Pause the recording, try it, and resume to check your answer. Okay, there's the graph, and it does indeed pass the horizontal line test, so g of x has an inverse. In this case, we're going to make sure it has an inverse, and then if it does, find the inverse. Notice that we are restricting the domain here. Y is greater than or equal to negative 3. X is greater than or equal to negative 3, and y is greater than or equal to 0. So when you graph it, make sure you impose those limitations on your graph. Pause the recording, give it a try, and resume to check your answer. Okay, this does indeed have an inverse when you graph it and you limit it to the numbers they gave you. This is to ensure that our inverse is not going to end up with a negative under the square root. And we switched x and y, took square root of both sides, and then subtracted 3. You may be wondering why we didn't do a plus or minus. And again, it's because of that restriction. Y is going to be greater than or equal to negative 3, so there's no need to put a negative in front of the square root. Okay, same song, second verse. Try this problem. See if it has an inverse by graphing it, and then find that inverse algebraically. Pause the recording, try it, and resume to check your answer. Okay, here it is. We didn't show all the steps here. There they are. First of all, swap out the x and y, and then we multiply the bottom by both sides. Distribute, get all the y's on one side, factor it out, and divide. This time you're going to restrict the domain. The easy way to do this is to graph it and then look at it and realize that we don't want a horizontal line to hit it in more than one spot. So figure out where would be a good place to start x or to end x, and then find the inverse and state the domain and range. Pause the recording to do this and resume to check your answer. So the domain, x is going to be greater than or equal to negative 2. Remember, an absolute value looks like a v, so what we want to do is we want to restrict this to just one side of the v. The range is going to be y is greater than or equal to 0. Okay, then we're going to swap out the x and y, and since we're limiting the domain, we really only have to deal with that one line, so we can kind of ignore the absolute values. Just solve for y, and we get x minus 2. The domain of our function, we restricted it to x is greater than or equal to negative 2, meaning the range would be y is greater than 0. When you do the inverse, the domain, the range actually flip-flops. So now our domain is going to be x is greater than or equal to 0, and the range is y is greater than or equal to negative 2.